Thank you, Jan. Thank you, Matthias and Jeremiah, for organizing this truly amazing workshop. And being the last talk of the day, I'm going to start relatively simple. And before diving in, I'm going to ask maybe a simple question. And the question is, can I train a Bayesian neural network to distinguish expensive art from children's drawings, which I'm not arguing are not art, but I'm probably not going to get very rich by selling my niece's drawings. So we'll start as we would start training any algorithm, and we are going to collect data. So we suppose we are scraping Google Images, we collect some drawings of children, and then to get some expensive art, we are going to look at artwork from the National Gallery here in London. Good, I've collected some data. Now I'm going to show my Bayesian neural network some drawings of children, and then other works that it was not trained on from the National Gallery here. And as you would imagine, nothing surprising is going to happen. It's going to be relatively really good at predicting which of those are going to get me rich if I sell them and which of those no. Now, suppose I'm going to show now my Bayesian neural network an image of Miro. Actually, what is happening in reality is that my Bayesian neural network is going to say, listen, you are not going to get any richer by selling this. Now, of course, that's not the case. And something went wrong here. The thing that went wrong is I give it something that I didn't train it to predict, because the National Gallery here in London does not have modern art. Okay. So to understand what's going wrong in this model, what we are going to do, we are going to revisit first, very, very briefly, the classical Bayesian model, because I trained the Bayesian neural network. It should have been fantastic in predicting uncertainty, but instead it was extremely certain that the Miro art piece is not expensive. So in the classical Bayesian model, what we're having is that we are treating the parameters as random, sure. But the covariates, we are fixing them. We are treating them as if they were not coming from any distribution, as if they were given to us. And by doing so, what happens is that the posterior distribution in our data, which depends on the prior is independent of the data, because, yeah, sure, the data is given. And therefore, even if I'm going to show you a new data point and I'm going to still treat it as different, but sorry, I meant to say I'm going to still treat it as fixed, what is going to happen is that my posterior is not going to change upon observing the new test data point. So seeing the image by Miro would change nothing. What I actually want to do, I want to be able to estimate predictive uncertainty well. I want my Bayesian neural network not to tell me, yeah, I'm absolutely certain that Miro is not an expensive work of art. I want it to reflect the actual uncertainty it should have presented. It should have said, hey, it's not really similar, not to the children drawings that I saw, not to the artwork that you showed me. I should be somewhere around the decision boundary, which is definitely not at zero. Now, when we are talking about predictive uncertainty in Bayesian terms, what we are doing is to actually integrate over the posterior. And as we just discussed, the posterior is unchanged. I introduced it to the new data point. I showed it my X star, nothing happens. And what I'm going to do today, and maybe it's the only place I can say it out loud, is kind of break the Bayesian model. And I'm going to say, really? Does looking at X star, which we might assume that is coming from a different distribution, should really not change the uncertainty that I have? And when I'm saying that my new data point is different, you all felt really comfortable with me saying the words distribution shift before. But the moment I say distribution, this also means that I should treat my data, my covariates, as random. And if I'm treating them as random, I might as well kind of throw away or maybe extend, depends on how you want to look at it, the classical Bayesian model. And if I'm allowed to treat my covariates as random, I might as well assume they do have some influence on my model. And the moment I assume that my x's are random and they do influence theta, what happens is that my prior now becomes P of theta given the training data and the new covariate. And this is kind of going to be my main point here today. By allowing my prior to depend on the new test example for which I'm going to try to make a prediction, by doing that, I'm going to be able, in a sense, to capture the uncertainty I would like to. But at this point, you should say, wait, that's weird. How, by just observing the covariates, you're gonna know that your prior should change? So let's look at a very simple example. Let's say my training data is just 2 covariates, my y's are binary, I'm gonna fit a logistic model, but note that here on the second column, all my observations are of the same value. This means that I actually don't, if I'm fitting the logistic regression model, I don't care how I divide my weight between the intercept and the coefficient of that constant column. Then I'm going to observe my test data. And note that even if you do not observe the y's, just by knowing that if the second feature that I have now is changing, it means that you already know, without knowing anything about y, that you do care now how the weight is distributed between the intercept and the coefficient of the second feature. Meaning, before you observed y, in the prior, you already assumed that the prior should depend on the new data. So if we actually do that, we need to define a prior. And I want to define a prior not for that specific problem. I want to define some general prior. I want to be able to define a prior that is adaptive to my test data. And a very easy and intuitive way to do it is just to say, hey, I'm going to define an energy function. I'm going to give this an energy function, the likelihood, both of the training data, and now the new covariate. And I'm going to define my prior based on that. So how does it look? I'm going back to the example from the previous slide. And as I said, you're looking here at the intercept and the second coefficient. In the beginning, before I observe my test data, I don't care. There are a lot of combinations that are as likely. But as I begin to start to add data points, what is going to happen is what you would expect. I'm going to get more and more concentrated around the value that actually corresponds to the test data that I showed you in that point. Okay, good. Hopefully, I convinced you that an adaptive prior is something reasonable. And I showed you how I define an adaptive prior. But I'm reminding you that what I actually wanted is the posterior. But the posterior, of course, depends on the prior. And this prior now is adaptive. So, hey, I got an adaptive posterior. And the reason an adaptive posterior is important to us is because I'm not the first person to talk about distribution shift. People have been around and working on that for a while. But what is different is that usually this is treated by taking some predefined distance notion. They say, okay, the image of mirror in some distance looks differently than the images that I have observed. But is it the relevant distance notion? Does it capture whether it actually affects my ability to predict? Because I can give you something that is different, but I will still be able to predict for well. To now use this posterior, this thing that does capture the correct notion of distance, what I'm going to do is actually to specify an amortized posterior. I'm going to set it to be a function of x star, and therefore I'm going to approximate the true posterior in a way that I can evaluate it at different x stars. So, unsurprisingly, especially in light of the previous talks today, I'm going to do variational approximation, which means that I need to specify the family, the variational family I'm going to use. And unlike the 2 previous talks, I'm going to just put here something really standard. I'm going to just take a Gaussian with some diagonal covariance, and I'm going to fit the mean and the covariance of that Gaussian. Now, as have been discussed here in length, this scale divergence is intractable, but this is a small hiccup for us. We know that we can optimize the elbow instead. And all it remains for me to do is to learn the parameters of that variational distribution. One way to do it, and a very flexible one at that, is I'm going to take both my training data and the new covariate that I'm now getting. I'm going to put them through some embedding pre-trained on my training set. I'm going to get embeddings, but I don't want to work with all the embeddings of the training set. So those I'm going to aggregate. I'm going to take both of them, feed them to a neural network that is going to output for me the parameters of my variational distribution. I'm going to sample from that distribution. Now I have finally my data. I can assign it to my model, predict, and fit the elbow. And if indeed you have that X star already in your hands, this should be the end of my talk. But usually, when you are training your model, you don't have access to shifted data. If you would have trained on that. So what do I do if I don't have this X star when I'm training my model? And in the interest of time, I'm not going to go into the details of that. But what I am going to do, I'm going to tell you about a simple idea, and we have the proof, and I'm going to skip it, but I'm going to tell you what the idea is based on. And the idea is kind of the inverse of bootstrapping. In bootstrapping, you take large samples, and those samples should approximate the original distribution of the population. What I'm going to do is to do the absolutely opposite. I'm going to take small subsamples from my training data. Now, since they are small and the variance is large, the empirical distribution of each of those subsamples is going to be different. And this different empirical distribution is going to be a simulation of a possible shift. Now, the true test data exists, and it's going to come in some time, and it has some distribution. And the thing that guarantees to me that I'm going to be able to approximate that shift as well, is that I'm going to take a lot of subsamples of small size. And by taking such large number of subsamples with very, very high probability, I'm going to be as close as I want, except of 0, to the true distribution that I'm going to observe at this. But one thing that I still wouldn't know is which of those my small subsamples is the one that approximates the true test set that I have never seen and know nothing about. And the answer is I will never know. But one thing I can do is to make sure I'm doing relatively okay on each of those small subsamples. And if I'm doing relatively okay on all of them, then I will be able to do relatively okay to something that is epsilon close to that. So, okay, how do I ensure that I'm doing relatively well on all of them? Well, actually, there is a whole field about it, and it's called out-of-distribution generalization. And the main trick this field uses is that says, let's penalize for differences across those synthetic environments that we are creating. So now I have a way to simulate those shifts, and I have a way on each of those shifts to learn a posterior that is adaptive, which means that I should be able to catch the actual structure of uncertainty in my data. And I have been selling you so hard on this weird idea, so I at least should show you that it actually works. And as you can see here, what we have is just a simple heteroscedastic regression in one dimension. And what the uncertainty should look like is that it should go like conus, because I have truly have more variance in the data as x's go larger. And although that there are many other ways to quantify uncertainty and to handle distribution shifts, actually the only thing that actually captures this very simple but yet very complicated for a neural network structure of covariance is the one based on the posterior. And the main take, we have similar results for other examples as well, and on real data too, which I'm not going to bore you with, but if you'd like, I'll be happy to tell you about it. But the main thing that I want you to take from here is that by allowing ourselves to treat the covariates as random, And by allowing ourselves to actually fit a posterior that treats them as such, we are able now to capture the true levels, or approximate as well as we can, the true notion of distance, and therefore the true levels of uncertainty. Thank you.
Do we have any questions?
Thanks very much for that talk. I wonder if you might go back to the previous slide, or the one with the code.
I would, but it's stuck. Okay.
So I think it is clear that in terms of the uncertainty in the test data, it's outperforming the rest. I was just very curious on what the uncertainty in the training set is doing, because it seems like it's a bit almost over dispersed. It's quite wide.
Why is it wide right here?
Yeah, so on the left-hand side, it's seems like you're sacrificing something.
You're always sacrificing something, because the way that you are doing that is to say, hey, I'm expecting variance in my data. Shifts are possible and I have to be able to account for them. And the moment you're doing that, definitely you're sacrificing something. But to be honest, I kind of gave you the worst performance of our method here, because here in this specific example, the variance grows relatively very fast. But in the paper itself, we have like smaller levels of variance, and then you still need to sacrifice something, but it's proportional to how fast the variance is growing. But the interesting thing in this, and also in this example, is actually not the, okay, we are outperforming existing methods. Put that aside. The interesting thing is that other methods don't catch the right structure. More variance, less variance, this I can live with. But if I don't know to tell you in advance in which areas of my data I should expect high uncertainty, and sure, the uncertainty can be a bit lower, a bit higher, but I don't even know how to identify the correct areas, then the game is lost.
And in terms, if I may ask, are there any sort of functional assumptions you need on the type of ones you're trying to fit? So regularity.
So yes, we need slight regularity conditions. The moment that we need them is to ensure that I can actually learn this posterior that I'm talking about, which means that we need convergence rates to be okay-ish, but nothing out of the ordinary. I'm happy to tell you the details of how we improve.
Time maybe for one more.
Okay, thank you for the talk. My feeling is that in Bayesian neural network data somehow kind of capture your prior on the hypothesis class, right, from X to Y, not necessarily on X. So now you allow this prior dependent on X. It's kind of saying that when you observe new X, you are kind of changing your hypothesis class. That's my feeling. So is that something that you would say in that way?
I don't see it that way. I'm gonna try to tell you why.
Okay.
In the classical Bayesian model, when you are assuming a prior on theta, you are saying you're not restricting it. Yeah, of course, you can put a prior that puts zero mass somewhere, but in a sense, you are looking at the parameter space, not at the hypothesis. So it's a very simple example. If your model is a regression, then of course you can say now my coefficients come primarily from some area, or maybe only if you put actual zero mass on other areas. But you're not restricting the hypothesis class. Your hypothesis class is still the regression model that you have. And when you're allowing your prior to depend on the data as well, you are not altering the hypothesis set. What you are altering is in the parameterization of this hypothesis, which instances of this class are more probable than others.
Yeah, but that's kind of like a soft kind of modification. I'm not saying it's hard, but I'm saying the soft one.
Can you
In the
explain?
sense that you are not saying you exclude certain coefficients,
Mhm.
but somehow you change the probability that the coefficients will get into your.
I definitely change the probability. This is kind of the point, because what I'm trying to say is that I should be more uncertain or less uncertain depending on the data that I have at test time and how it compares to the data I had at training time. So for each different example, for the mirror image or for another painting, I should get different plausibility of instances in that hypothesis test. I should prefer some of them more and some of them less.
Well, thank you very much once more. So now we can all go upstairs. There'll be some drinks, there'll be some posters. If you are presenting a poster, come find me. I've got some things for you. And everybody, please stick around because they're super exciting.